Hey and welcome. We're diving straight in with your ultimate power revision for the mandatory experiments that you absolutely have to know for your junior cycle science exam. We're not wasting any time. This is all about the high-yield info that's going to get you those top marks.
All right, let's just get right to it. This is the big question, isn't it? You're putting in the hours, you're reading the textbook. So what is the secret sauce? What's the thing that separates a good grade from a truly great one?
You know, it really is as simple as this. Your exam is guaranteed to test your practical knowledge. So if you can walk in there confident that you can describe the equipment, the method, and the results for these key experiments, well, you're not just studying. You're building a rock-solid foundation for that top grade. And that's exactly what we're going to do right now.
So here's our game plan. We're going to start with the world of particles, then see them in action with changing states and cooling curves. After that, we'll hit some key chemistry experiments, run a super-fast lightning round through physics, bio, and earth science, and then finish up with a winning exam strategy. Let's do this.
First things first, the world of particles. Look, pretty much everything in science, from a solid block of ice to the air we're breathing right now, it's all made of tiny, tiny particles. And if you get how these particles behave, you've basically found the master key that unlocks almost every other topic.
So let's break this down. In a solid, all the particles are locked into a neat, regular pattern, kind of just vibrating on the spot. Then you have a liquid, where they're still packed in close, but they can now slide past each other. That's why liquids can flow. But a gas? Oh, the particles are super far apart, zipping around all over the place. And here's the key takeaway. That huge space between gas particles is exactly why you can easily compress a gas, but you just can't do that with a solid or a liquid.
Right, and because those gas particles have so much space and energy, they don't stay put, they spread out. We call this process diffusion. Just think about spraying perfume or deodorant in a room. All those particles start in a high concentration right by the can, and then move out to a low concentration across the room until you can smell it everywhere. And this happens way, way faster in gases than it does in liquids, like when you see a drop of food coloring slowly, almost lazily, spreading out in a glass of water.
Okay, so that's the theory down. Now, let's see how all this builds into one of the most common experiments you are definitely going to face, plotting a cooling curve. We're taking those abstract ideas about particles and putting them into a real graph you have to be able to draw and explain.
Honestly, the method for this could not be more straightforward. All you do is melt a substance, something like cetyl alcohol is perfect, then you pop a thermometer in it. After that, you just sit back and record the temperature every single minute as it cools down and turns back into a solid. The last part is just plotting those numbers on a simple graph of temperature versus time. Easy.
But when you plot that graph, you're going to notice something really weird. Just as the liquid starts to freeze and become solid, the temperature just stops dropping. For a few minutes, the line on your graph goes completely flat, creating this plateau. So the big million-dollar question the examiner wants you to answer is, why on earth does that happen?
And here's the beautiful bit of science behind it. Even though the test tube is constantly losing heat to the cooler air around it, the substance itself is releasing energy. As those particles lock into their new solid structure, they form bonds, and that process gives off heat. This energy release perfectly cancels out the heat being lost, which keeps the temperature totally constant until every last drop of that liquid has become solid. So cool, right?
Okay, time to switch gears into a little chemistry block. We're going to nail two absolutely essential separation techniques and a really fundamental experiment on what makes reactions go faster. These are total must-knows for the exam.
First up, distillation. This is basically how you separate a liquid solvent from a dissolved solid, like getting pure water from salt water. You start by boiling the salt water. The water evaporates as steam, but the salt gets left behind. Then, that steam travels into the most important piece of equipment here, the Liebig condenser. It has a cold water jacket around it, which cools the steam down, turns it back into pure liquid water, and then you just collect it at the other end.
Next is chromatography, which is just a really clever way to separate mixtures. Like all the different colored dyes hidden inside black ink. You put a small dot of the ink on some special paper, then you dip the bottom of the paper in water. As the water soaks up the paper, it carries the dyes with it. But here's the trick. The dyes that are more soluble, the ones that dissolve better, travel further up the paper. And before you know it, that single black dot has separated into a rainbow of all its different colors.
All right, now for reaction rates. There's one golden rule you have to burn into your memory. If you want to make a chemical reaction happen faster, you need to make the particles collide more often. And one of the simplest ways to do that is to increase the surface area.
And this is the classic experiment that proves it perfectly. You take some large marble chips, drop them in hydrochloric acid, and yeah, it fizzes and produces carbon dioxide gas. But if you take the exact same mass of marble chips and crush them into a powder first, the reaction is way, way faster. It's so much more dramatic. And why? Well, that powder has a massive surface area compared to the big chips, which means way more particles are exposed to the acid at once, leading to more collisions and a faster reaction.
Okay, deep breath. Time to switch gears for a lightning round. We're going to fly through the absolute essential experiments from physics, biology, and earth science. So pay close attention, because these topics come up all the time.
First up in physics, Hooke's law. In physics, Hooke's law. This whole experiment is about how a spring stretches when you apply a force to it. The method's a piece of cake. You hang a spring, measure its length. Add a weight, measure it again. The most important calculation is finding the extension, which is just the new length minus the original length. You just keep doing that with more weights, and then you plot a graph of the force you added versus the extension you measured.
And what you get is this really neat, satisfying result. Your points will form a perfect straight line that goes right through the origin of the graph. This proves that the force is directly proportional to the extension, and it gives us that famous little formula, F equals K times X.
Next, refraction. All this is light bending when it moves from one thing to another, like from the air into a glass block. It does this because it changes speed. And the rule is super simple and you just have to remember it. Light slows down and bends towards the normal line when it enters the glass, and then it speeds back up and bends away from the normal when it leaves.
Now for biology, you have got to know your food tests. This is pure memory work. For starch, you use iodine and it goes blue-black. For reducing sugar, you use Benedict's solution with heat and it turns brick red. For protein, it's the Biret solution, and you're looking for a violet or purple color. And for fat, the easiest one of all, just rub it on some brown paper and it'll leave a translucent spot behind. You just have to learn them.
And finally, for earth science, the greenhouse effect. This super simple experiment shows it perfectly. You take two jars, one with just normal air, the other with extra carbon dioxide, and you put them both under a heat lamp. And as the chart here clearly shows, the jar with the greenhouse gas, the CO2, traps way more heat and ends up at a much higher temperature. Simple as that.
Phew, we have covered a huge amount of ground here. You now have all the key knowledge for these crucial experiments. But before we finish, I want to leave you with one final piece of advice. This is maybe the single most important strategy you can use when you're writing about experiments in your exam.
And here it is. This is the absolute game changer. When you're asked about an experiment, always, and I mean always, draw a clear, simple, labeled diagram. It's just like the slide says, a good diagram can often get you more marks than a whole paragraph of writing. Why? Because it proves to the examiner in a split second that you know exactly what the setup looks like. It's the fastest way to secure marks.
So there you have it. You've got the methods, you've got the results, and now you've got the winning strategy. The only thing left to do is to actually put it into practice. So my final question to you is this. Which experiment's diagram are you going to draw and master first? Is it going to be distillation, Hooke's law? Pick one and get drawing.